Okay, good morning everyone. Today we'll begin chapter or section 7.6. We'll be looking at the natural base, or base E. I'll show you what that is in just a second. We have worked with other bases like base 2 raised to the x, with the inverse being log base 2 raised to the x, or of x, I'm sorry. We've worked with like base 3 raised to the x, with the inverse being log base 3 of x, and then the common log 10 raised to the x, with the inverse being log base 10 of x. Okay, so today we're going to be working with base E. So what is E? It's just not a letter, it is a number. So to get at what E is, let's take a look at what we have worked with before. Compound interest formula, which says that the future amount is equal to the initial amount times 1 plus the interest rate divided by the number of times interest is compounded, be it yearly, monthly, daily, and then raised to those number of periods times t, the number of years. So let's ask this question. What happens if P is a buck? We're going to invest a buck. It's going to be invested at 100%. So R is going to be 1. And we're going to invest only for 1 year. So T will equal 1. All right. So our equation then will be P is just 1 plus 1 over n raised to the n. Again, actually it just reduces. P is just 1. I could just say it's f of n is equal to, well, P is just 1, so 1 plus 1 over n raised to the n. Okay, what happens to our $1 investment as the number of compounding periods changes or increases? So let's take a look at that. Well, I created a table. Okay, so when the number of compounding periods is 1, we just have 1 plus 1 over 1, which is just 1 raised to the 1, which is just, so that's just 2. But when the number of compounding periods increase like to 100, so we have 100 compounding periods in a year, now we get a value of 2.7048. If we have 1,000 compounding periods in a year, 2.7169. As you can see, as the number of compounding periods increases, this value here is getting close and closer to some limiting value. At 10 million, for example, the value is about 2.7182817. So it seems to be reaching a limit. Okay, in the limit we call that E. So E is approximately 2.7182817. Okay, and we formally define E as the limit as n goes to infinity. The limit as n goes to infinity of 1 plus 1 over n raised to the n is equal to E. Okay, mathematically that's how E is defined. But the value for E is 2.7182817, and it doesn't repeat as an irrational number like pi. As n gets very large, interest is continuously compounded. Examine the graph where f of n is equal to 1 plus 1 over n raised to the n. The function has a horizontal asymptote. You see it reaches a limit. The y value reaches a limit, and that horizontal asymptote is the value y is equal to E. As n becomes infinitely large, the value of the function approaches approximately 2.7182818, and I showed that up here. All right. This number is called E, like pi. The constant E is an irrational number. Exponential functions with E as a base have the same properties as the other functions we have studied. The graph of f of x equals e raised to the x's, like other graphs of exponential functions, such as f of x is equal to 3 raised to the x. The domain, okay, like the other ones we have said, was all real numbers. The range is y is greater than 0. My horizontal asymptote would be y equals 0. Here I completed a table for e raised to the x. I chose values from -2 to 2. So e raised to the negative 2 is 1 over e squared, and that's equal to 0.135. Now, I'll show you that you do have, your calculator has a built-in function for e. So let me show you. Okay, right here, you see something called ln, and we'll see in a minute that ln is the inverse of e. But here, so right there at the ln, I see of e to the x. It's blue. It's blue. So if I want to evaluate e raised to the x, I have to go second ln, e raised to the x. Okay. Now, if I looked at my table when x was negative 2, if I go negative 2, e raised to negative 2, which is just 1 over e squared, that's 0.135. At negative 1, so again, second e raised to negative 1, that is 0.3678. Okay, if I go e raised to 1, well, that should be approximately 2.718281828. And again, it doesn't repeat. It's an irrational number. So that's how I completed that table. But like before, e has an inverse. And to graph the inverse, we just switch the x and y's as before. So now my y's became my x's, and my x's became my y's. But the inverse function for e raised to the x is the natural log of x. So let's look at that. A logarithm with a base of e is called a natural log, and is abbreviated ln rather than as log e. Okay, so we never write it like this here, log base e of x. Oh, I'm sorry. We never write it that way. I never want to see you write it that way. That we use the natural log of x. Okay, so natural logs have the same properties as log base 10 and logarithms with other bases. The natural log of x is the inverse of the natural exponential function e raised to the x. The domain for the natural log would be x is greater than 0. The range would be all real numbers. We'd have a vertical asymptote at x is equal to 0. So you see there, that graph never crosses the y-axis. Vertical asymptote at x is equal to 0. Inverse properties of e raised to the x and natural log of x. Okay, just like before, we've said that log base b of b raised to the x is x, and then b raised to log base b of x equals x. Okay, the properties, inverse properties for base e work the same. So e raised to the natural log of x is x. The natural log of e raised to the x is x. All the properties still hold. So for example, we have the natural log of e raised to 0.15t. So that just cancels out, and we have 0.015t. E raised to the 3 times the natural log of x plus 1, we have to undo the power property. So e raised to the natural log of x plus 1 cubed. Well, again, that cancels out, and we're just left with x plus 1 cubed. And then we have the natural log of e raised to 2x. Well, that's just going to be 2x. And the natural log of e raised to the x, that will just be x. And so we'll get 3x. We could have just as well used the product property. So we could have multiplied. That would have been the natural log of e raised to 2x times e raised to the x, which would have been the natural log of e raised to the 3x. Remember, when you multiply powers, you add the exponents. So we were multiplying base powers, if you will, but we add the exponents. 2x plus x is 3x, and that equals just 3x. Inverse properties. Right? You see the properties for logarithms still hold. All right. So applications of base e. So recall that the compound interest formula A is equal to 1 plus R over N raised to the N times T. A is the initial amount, P is the principal, or A is the future amount, P is the initial amount, R is the annual interest rate, and N is the number of times the interest is compounded per year. Well, what happens if interest is compounded continuously? And that's somewhat difficult to see, so we're not talking about every year, or every month, or every quarter, or every day, or every hour, or every second. We're talking about continuously. Well, if that's the case, if interest is compounded continuously, that there reduces just to that with base E. The formula for continuously compounded interest is A is equal to P times E raised to the RT, where A is the total amount, P is the principal or the initial amount, R is the annual interest rate, and T is time in years. So what is the total amount of an investment of $500? The initial amount is $500. We're going to invest that at 5.25%, so 0.0525, and for 40 years. Using our calculator, we would get 4,083. So I'll just do that. So show you how. So that was 500 times, okay, second E, and so that was what, 0.0525 times 40. Is that what they gave us, I think? And voila. So 40,083.08. What is the total amount for an investment of $100 invested at 3.5% for 8 years? So again, the initial amount is 100. We're going to invest that at 3.5%. And for 8 years, and we would get approximately $132.31. Now let's ask, how many years will it take for an investment of $1,000 to grow to $5,000 if it's compounded continuously at 3%? So again, we're working with the equation A is equal to, future amount is equal to the initial amount times E raised to the RT. So our future amount is going to be 5,000. Our initial amount is 1,000. We're working with E, continuous compounding. The rate is going to be 3% or 0.03, and we want to know how many years it's going to take $1,000 to grow to 5,000. So we divide by 1,000. So that will give me 5 equals E raised to 0.03t. I want to get rid of base E, so we have to take the natural log of both sides. The natural log of 5 equals the natural log of E raised to 0.03t. So that will cancel out, and we'll just have the natural log of 5 equals 0.03t. We'll divide by 0.03. And then that will give us approximately the number of years that will take that investment of 1,000 to grow to 5,000 at 3% compounded continuously. So natural log of 5, oops, clear. Natural log of 5 divided by 0.03, 53.64. 53.65. So let's say 54 years. Okay. 54 years. I could ask this question: what rate would be required for the $1,000 investment to grow to $3,000 in 20 years if interest is compounded continuously? With this problem here, I was looking for T. Now I'm given T, I'll be looking for R. So again, so we'll have 3,000 equals 1,000 times E. I don't know what R is, that's what we're looking for, but we have what T is. Okay, so if I take if I divide both sides by 1,000, I'll get 3 equals e raised to 20r. I'll take the natural log of both sides because I want to get rid of the e. So natural log of both sides. E raised to 20r. So that cancels out. Now I just have the natural log of 3 equals 20r. I'll divide both sides by 20. And then that will give me the rate that will be required for that initial investment of 1,000 to grow to 3,000 in 20 years. So the natural log of 3 divided by 20. So about 0.0549 or 5.49%. All right. That was solving for R or T. Or R, I'm sorry. We're solving for R with that one there. This one we were solving for T. This one we were solving for R. But the process is the same. All right, now let's look at this here because this is interesting. So this illustrates the coronavirus spread in the U.S. The U.S. is struggling to keep the virus under control as new cases are reported each day. Gray bars represent the number of new cases reported each day. Okay, the dashed red line shows the 7-day moving average, so they're just averaging on prior 7 days. As you can see that the 7-day moving average has been increasing tremendously. On April 13th, it was 40,000. By January 13th, 9 months later, it was 250,000 cases reported each day. We could ask this question: what has been the daily growth rate in new COVID-19 cases per day? So let's answer that. We're looking for R. Okay, so we know that the future amount, well, that was 250,000 cases reported per day. We started at 40,000. I started at April 13th approximately, so that was 40. E raised to the R, which is what we're looking for. And T, we're talking about days, and that was a span of 9 months from April 13th to January 13th. Let's say there's 30 days in a month, so that would be 270 days. Okay, we can find R. I can divide by 40. And so that will give me 250 divided by 40. That would be 6.25. Equals e raised to 270r. I can take the natural log of both sides. Equals natural, which will get rid of the e on the natural log of e raised to 270r, so that cancels out. So now I have the natural log of 6.25 equals 270r. If I divide by 270, let's do that with the calculator. Natural log of 6.25 divided by 270. 6.25 divided by 270. So 0.006. I'll show you. I'm going to store that. So where's my store key? How can I store that? I don't see. Oh, my store button right there. So I'm going to store that. And I'm going to store my answer in a variable a, so I'll just go alpha a. I'm going to store it in a because I'm going to use that. So I'll store that, but 0.006787. Okay, so 0.006787, I believe is what it was. 6787 equals. Okay, so the total number of reported daily cases in the U.S. has been a little less than 1%. Okay, a little less. The growth has been a little less than 1%. So my equation then would equal A equals P times E raised to the R, which is 0.006787T. All right, we found R. Sometimes you have to find R first. Now we can answer the second part of this equation. If this rate continues, what would be the expected number of new cases per day in the next 100 days? Well, our initial amount is going to change. We're not going to start at 40 because we're talking about the next the next 100 days. So we're going to start at 250. Okay, we're going to start at 250. So here, this is going to be then A equals 250 times e raised to 0.006787, and we said time the next 100 days, so this will be 100. Okay, we're starting at 250 now. So let me do that. So that's going to be 250 times, so second. Now what I'm going to do, because I stored that in my variable a, I'm just going to go alpha a. I'll show you. I like to alpha a, CA, and then times 100. So about 493,000 daily cases. So if the rate of growth and the number of reported cases, daily reported cases of COVID-19 in the United States continues at the same pace, 100 days, rather than 250,000 reported cases, we will have 493,000 reported cases. Guys, we'll never be back in school. And that's what makes this virus such a pain. And unfortunately, the new strain of virus is even more contagious than the other strain. Not good. We got to do something. Mask up. Vaccines or something, because this is out of control. Right? So they're a good application of log functions and exponential functions in base E.